stream on YouTube.
Okay. Okay, let's see. Give me a second.
Yeah, sure.
Oh, okay. You guys see my screen?
Yeah, I do.
Okay. I guess 5 minutes might be too generous. I guess what I heard
Yes,
from
maybe we
Berkeley is
can.
that actually, like, if the class starts at 2, like, professor goes there by 2:10 because students just don't come in like 10 minutes.
Yeah. Yeah, okay, great. So it is live stream on YouTube, so we can start probably now. Okay, hello everyone. Welcome to today's Quantum Matter seminar. Today it's our great pleasure to have Professor Jong-Yeon Lee from University of Illinois, Urbana-Champaign. Professor Lee received his bachelor's degree in Caltech and got his PhD from Harvard in 2020 under the supervision of Ashwin Vishwanath. His PhD research focuses on various of exotic phenomena in many-body physics, like the topological band theories and anomalous response to fractionalization and gauge field. And later, he became a postdoc fellow at Kaplan Institute of Theoretical Physics, where he pioneered the physics of decoherent quantum many-body system, which he will talk about today. And since last year, he moved to University of Illinois as an assistant professor. Okay, it is your turn. And for the audience, if you have any question, please use the raise your hand function. Right, thanks.
All right, yeah, I'm Jong-Yeon, and I thank Iju to invite me for this the great seminar. So today I'm going to talk about many-body physics of information. So in the study of many-body physics, one of the central themes is to study robust or universal phenomena emerging at large-scale systems as a consequence of interactions among lots of degrees of freedom. In such a study, often what we care is physical properties that are robust under such perturbation. For example, like when we classify this phase of matter for water into like liquid, solid, and gas, this like when we are in a certain phase, like those like notional phases kind of robust under small perturbations. Similarly, in this like quantum phase of matter, like if you're in a say a superconducting phase, then even if you perturb your temperature or doping level a little bit, you're still gonna be in the superconducting phase. So really, like in the many-body physics, what we care is this robust kind of behavior. And if we think about this, like robust behavior can be used as a like really a pieces of information. For example, we can imagine having an array of containers with like a temperature control. and each container has either like a water, liquid, or ice phase. Then this array of containers basically represent a certain bit string of information, which is robust under small perturbations. Accordingly, these phase labels provide a way to store classical information in a robust manner. And along this line of thought, one can ask whether there exists any classical or quantum information that can be stored robustly in the many-body system. So under this many-body physics of information, instead of looking at conventional physical quantities like conductivity or magnetization, I'd like to look into more abstract quantities like entanglement pattern or some hidden correlation that requires some decoding or post-processing. Ultimately, the goal here is really to understand robust or universal information theory quantities emerging at large-scale system. So to begin with, let me make a few remarks about what's different from more of a conventional setting. So when it comes to really, so here I'd like to think about coupling to environment as a kind of essential ingredient, because any unitary perturbation within the system cannot remove or add additional layer of information. So two most representative examples of this coupling to environments are measurements and decoherence. They are actually very similar, but the difference is that in measurement, wave function collapses in a way consistent to the observation. So measurement acts more like a way to extract the information. But in the case of decoherence, some environment measures your system in a way that's unknown to the observer. So the system becomes mixed and it's basically losing information. So for you who may not be familiar with this decoherence, the idea is that environment randomly applies some a local perturbation such that the system initially starting from size 0 evolves into a mixed state with which is given as ensemble of different states, each of which is given with some probability. A more compact notation might be using Krauss representation, where each psi I is given as some operator ki times psi 0, and each Krauss operator comes with this probability pi. So if I give us some brief summary of today's talk, it's really asking what happens to quantum many-body states under decoherence. And as I said, pure state will evolve into mixed states, and most of the physical observables would non-local observables would decay exponentially, so that in the thermodynamic limit, many of the interesting physical observables kind of become unidentifiable. So one may ask whether there is any transitions, and I'm claiming that there is really a transition in the information theoretic quantity. And this is not just abstract transition, because this transition in the this information theoretic quantity, there is certain decoding protocol where this transition behavior can be physically observed. So this is the outline. In the first part, I'm gonna talk about this. I'm gonna give you some concrete example of this information theoretic phase transitions under decoherence. And then the second part, I'll talk about some theoretical probe or some theoretical framework to understand this kind of transition in the mixed states. So as a motivation, I'll talk about a state preparation via measurement. So the idea is that if you combine finite depth unitary gates, measurements, and decoding operation, then you can prepare a long-range entangled state in a somewhat efficient manner. And the question is, if each of this ingredient is faulty, whether you can still prepare long-range entangled state in a robust manner. And this faultiness is really translated into decoherence in each of this procedure. So as I said, measurement is a way to extract information from quantum state. When you measure, the state kind of collapse into like certain basis following the Born rule, meaning that the probability of getting a certain outcome is proportional to the magnitude square of the coefficient. And if you think about it, then it is really a way to manipulate a quantum state in a stochastic fashion. So if you project your quantum state by measuring, then it will kind of stochastically kind of collapse into like one of two possibilities. And let's say if this a red wave function is what you want, then you can like repeat this like preparation and measurement until you get the desired outcome. In some sense, like I think quantum teleportation is the best kind of example for to convey the idea of manipulating quantum state using measurement. So in the simple example of like quantum teleportation, this is what's happening. So in like A, you have this like superposition wave function psi, and in B, it's initialized as simple state 0. And now, like you apply this controlled X gate, which is nothing but just like mapping this state into applying Pauli X gate on the second qubit if the first qubit is in a spin up state. In a state 1. So basically, what it means is that 0, 0 maps to 0, 0, but 1, 0 will map to 1, 1. Because Pauli X operator is flipping 0 to 1 and 1 to 0. So after this gate, it's entangled. Now you measure your first qubit in Pauli Z basis. So based on this like coefficient, you're gonna get outcome 0 and 1 with like probability A square and B square. And the second qubit will exactly follow the outcome of the first qubit. So there's nothing interesting here. But now, like let's say we measure the first qubit in the Pauli X basis. So you just rewrite the same state in this like eigenstate of the Pauli X basis. Then if the measurement outcome is plus, then you're basically teleporting qubit in the wave function psi into qubit B. And well, maybe then you can say that, oh, I'm gonna just repeat this experiment until I get measurement outcome plus. But actually, even if your measurement outcome is minus, it is just different by psi by just like up to Pauli Z operator. So if you perform this decoding operation condition on the outcome of measurement outcome, then you can like deterministically teleport your quantum state from A to B. So what it means is that if you just combine entanglement and measurement, it will manipulate your quantum state in a stochastic fashion. But if you combine entanglement, measurement, and decoding condition on this measurement outcome, it's going to manipulate your quantum state in a deterministic fashion. So now that we know basic about this kind of procedure, let's talk about like slightly more non-trivial example, which is a GHZ state. So this generalized GHZ state is superpositions of two components which are macroscopically different. The first component is just like string up 0, and the second component is string up 1. So this is like a very similar to cat state in the sense that like measurement of any single qubit will collapse your quantum state into one of the two components. So the idea is that instead of doing a like unitary time evolution to prepare the state, can we just like prepare the state by project onto some desired components? So because like this product state of plus contains kind of desired components, like there's a string up 0 and string up 1, if it's somehow possible to just project this out, then we'll be able to prepare a cat state. The reason is that preparation of this cat state is very difficult because it's a long-range entangled state, and preparation time, if you just apply unitary gate, will scale with the system size. So as a theorist, you may imagine there's a cat state projection operator starting from this product state. And this can be phrased as some kind of imaginary time evolution by this like Ising Hamiltonian, because all 0 and all 1 state will survive under this like imaginary time evolution. So experimentally, what you're doing is the following. You measure this ZZ operator for neighboring sites everywhere starting from this product state. And then you like throw away the wave function if the outcome is minus, and you only keep when like all the measurement outcome ends up in +1. And like by this procedure called the post-selection, in a sense that you're kind of selecting based on this measurement outcome, you can get a cat state. However, there are like two issues. The first thing is that measuring two-body operator is somewhat non-trivial in the sense that like when you're just shining a light onto individual atom, it's not going to measure like two-body operator. It's going to just measure individual like qubit. The second thing is that like according to this protocol, you have to repeat experiment on average exponentially many times because the probability of getting like outcome minus is like 50%, meaning that the probability of getting all measurement outcome to be 1 is like 1/2 to the n. The resolution for the first issue is actually pretty simple, which is commonly done in practice. So what you do is introducing ancilla qubit between every pair, and you entangle them in such a way that by measuring this ancilla qubit, the white qubit, you're actually getting information about this ZZ operator. So in some sense, this like white qubit is like measuring the domain wall of this red qubit. And in like a circuit diagram, what you do is applying control Z gate in this way, and then measuring the ancilla qubit. So then like in practice, this is the way you do. So this red qubit is the qubits that you want to prepare the GH state. So you introduce this ancilla qubit and you entangle them and you measure all these ancilla qubits. And if the measurement outcome is all plus, then you're preparing a cat state. However, as I said, this is still problematic. So to avoid the post-selection, I'm using the fact that this white qubit is really the domain wall configuration. So what does it mean? If I assign, say, spin up for the first red qubit, and if the measurement outcome in the second qubit is minus, then the third qubit must like point to the opposite direction relative to the first one, and so on. And the thing is that actually the first qubit is in a plus state, meaning that after all the measurement, it should be in a superposition of like a given configuration and totally opposite configuration. And now what we know is that like based on this domain wall like measurement outcomes, there are like some qubits pointing directions opposite to this reference one, the first one. So we know like where to like apply a spin flip. And after this spin flip, which is basically a decoding operation, we're getting this cat state no matter what the measurement outcome is. So pictorially, this is what I'm doing. Starting from this like short range entangled state between ancilla and the physical qubit, like if you get all the measurement outcome to be +1, you get desired cat state, but there are exponentially many different trajectories. So it's likely that you get kind of different trajectory. And if you think about, and what you're doing through this experimental protocol is really an ensemble of different quantum states. And this ensemble density matrix will just look like a maximally mixed state. However, the thing is that you know this label S, you know this measurement outcome. So if you apply this decoding operation condition on this measurement outcome, then like this decoded ensemble will be a pure like cat state. So in this way, you can implement this projection operator by combining this the finite type unitary circuit, measurement, and decoding. And so you can imagine this is really an imaginary time evolution. So this is a really well-known protocol, but one can ask whether this protocol is robust under deviations from the from ideal setup. For example, there can be some systematic bias on your kind of gate implementation, or measurement can be corrupted, or decoding operation can be faulty, right? So like we can ask, we can like divide this question into really 3 layers. The first question is whether each of this trajectory has a non-trivial correlation structure or long-range entanglement structure. Because decoding operation is a local operation, you cannot create long-range entanglement from the short-range entanglement by just decoding alone. And the fact that you can, if you want to create kind of long-range entangled state by decoding, each of this trajectory should have some long-range entanglement, although it may not be easily identifiable. The second thing is that now that we know each of the trajectories non-trivial, we want to see whether this decoding operation can be efficiently done. And finally, we want to generalize this idea to a broader class of quantum orders. So, to understand this like better, I first have to like expand some concept. So previously, I was like treating this white ancilla qubit as like a second-class citizen whose whole purpose is allowing us to measure some two-body operator between red qubits. But actually, when we entangle them in this way, they're forming some special class of short-range entangled state called the cluster state, which is actually a symmetry-protected topological order because this state is invariant under two like Ising symmetry operations. The first one is a spin flip on every even side red qubits, and the second one is a spin flip on every like a white qubits. So this is not just a short-range entangled state. This is a short-range entangled state with additional symmetries. And this SPT state is really characterized by this non-local order parameter. So if you can imagine any like a string of operators composed of like a two z's at each end on like odd sides and product of x on the even sides in the middle. And this operator takes the expectation value of 1. And what it means is that if you measure all the like x operator on the even sides, then you're gonna induce some long-range correlation between these odd sides. It can have some like plus sign or minus sign, but the important thing is that there is some long-range correlation. Because we are not like, while measuring the even side, because we are not like perturbing anything on the odd sides, because of the symmetry, expectation value of z should be 0, but it still have a long-range correlation, meaning that it must have a long-range entanglement. Any questions so far? Okay. So, and this kind of property is also kind of robust, even if like there is some systematic kind of perturbation that as long as those perturbations respect the symmetry. Under such a perturbation, this non-local order parameter will take like not a unit value, maybe like 0.6 or 0.5, but because that you have this like non-local order parameter for arbitrary lengths, like measuring all the even side qubit will still induce long-range entanglement. Now, another thing you can think about is what if the measurement outcome is corrupted? So although I can potentially introduce some error channel for every kind of ancilla qubit, like right now, let's model this by some kind of rotation error such that like your measurement is happening in some slightly off basis. So if you rotate every kind of ancilla qubit by angle theta and project them into measurement outcome kind of SI, then you can show that this state is mathematically equivalent to just starting from this product state and evolving it by imaginary time evolution with this Ising Hamiltonian and with like a beta given by this. So when theta is 0, this beta will go to infinity. So which means that this procedure is mathematically equivalent to kind of like infinite imaginary time evolution, which is just ideal projection onto the cat state. However, if you have any like error, like rotation error, then beta will be finite, and this will beta and then this like the correlation function of the like a final wave function will be captured by basically the StatMech model of one-dimensional Ising model at inverse temperature beta. But what we know is that in one dimension, Ising model has no long-range correlation at any like finite beta, which means that at any finite theta, there will not be long-range correlation. So each of the trajectory will be already trivialized. And similar thing happens if we have a faulty measurement. So let me just skip this quickly. So they are kind of basically very, very similar. The only difference is that the error rate P is related to the rotation angle theta by this equation. So when theta is 0, P is 0, but like theta is finite, P will be finite. So really the question now is whether we can prepare, long-range entangled state even under decoherence. And if you're familiar with the statistical mechanics, you may immediately say, oh, just go one higher dimension, right? Because in 2-dimension, Ising model has finite temperature transition. So instead of arranging this red qubits in one-dimensional array, you can arrange them in this 2-dimensional array and introduce ancilla qubit every kind of neighboring pair, and which is going to form 2-dimensional cluster state. And then you can measure every white qubit in X spaces. And if everything is ideal, like you can apply decoding operation, and this will implement a projection onto the cat state. And now we can introduce some rotation error, which is gonna map this imaginary time evolution to a like finite imaginary time evolution with 2D Ising model. And it actually is going to map to a 2D random bond Ising model because the sign of each kind of bond will be random because of the random nature of the measurement. But what you can show is that this 2D random bond Ising model is finite, still has a finite temperature transition, and this critical error rate or critical like angular deviation is actually pretty large, I would say. So now that we know like every trajectory or on average trajectories are very non-trivial, we can ask a second question, which is how can we decode kind of each trajectory into like the most representative one. So when there are no errors, the measurement outcomes are simply domain walls. So like we could just like flip spins based on this kind of domain wall instruction. But with errors, like domain wall configurations can be frustrated, meaning that it's not consistent anymore. So let's say the white color for this ancilla means like your measurement outcome is plus, and blue color means this measurement outcome is minus. And like this configuration is frustrating in the following sense. If I assign speed up for this qubit, then the one here will be also spin up because like there is no domain wall because this measurement outcome is plus and same. But now when we come back to itself by going through this pocket, it's gonna come back with a opposite sign, meaning that this measurement outcome is like not consistent. So in ideal case, actually, the product of this measurement outcome for each pocket should be +1. However, you can immediately identify that there are two pockets where the product of relative orientation is actually -1. So because like this pockets are frustrated, it's not immediate how to identify identify where the errors are and where the what the consistent assignment is. So the decoding becomes like solving an inference problem for given a pattern of frustrations. You're like assuming certain like probability distribution, and given this like faulty like measurement outcomes, you have to infer what is kind of most likely consistent assignment of the spin configuration on the red qubits. And then you have to apply decoding operation accordingly. So this is like how it's done in experiment. So you prepare there's a 2-dimensional cluster state, and then you like rotate by theta or apply some measurement error, and you measure those like ancilla qubits, and then you get some pattern of frustrations. And based on this, you're trying to infer what the most likely spin configurations are for red qubits. And then you're applying spin flips, and then you're going to get some mixed state density matrix, which has long-range entanglement in a sense that it's going to have like a zero expectation value for spin single kind of Pauli-Z operator, but it's going to have a long-range correlation of Pauli-Z operators. And also like product of X will be 1. So theoretically, I can show that individual trajectory is like long-range entangled as long as error rate is below a certain threshold. And this, and when it comes to decoding, actually, decoder must assume what the underlying error rate is to solve this maximum likelihood problem. So x-axis is the true error rate, and y-axis is error rate assumed by decoder. Then this is a decoding phase diagram one can obtain. So in this like red phase, you can decode some long-range entanglement out of this kind of decohered mixed state, but beyond you cannot. And like along this red line, meaning that error rate assumed by the decoder is equal to the true underlying error rate, you're having kind of the most maximal kind of threshold given by error rate of like roughly 11%. But like if your decoder assumes the error rate is like as small as possible, the error rate you obtain is actually the 0.103, which is slightly smaller than this PC, but which is good enough. And actually, maximum likelihood decoding, maximum entropy decoding is like doing a Monte Carlo simulation. So its time complexity is not guaranteed. But if you go to this blue dot, this decoding can be done by minimum weight perfect matching algorithm, which is the polynomial time complexity. So it has a kind of bounded time complexity, and it's much faster than this maximum entropy decoder. So there is a trade-off, but the point is that even if you decide to choose like a faster decoder, you're not losing that much. And this is the like numerical simulation result for this decoding problem. And you can see that like as I'm like increasing the system size, the square magnetization like undergoes a phase transition at this like a tentative like critical point. And what's interesting is that the variance of this kind of square magnetization is like only diverging at the critical point, meaning that like when you think about this, the disorder ensemble system doesn't know whether it's like long range ordered or not. But like once you're within the like dip in the phase, then system knows where it is, and across the disorder ensemble, there are basically no kind of variance. Like the variance would decrease with the system size. So now what I established is that there is some stability under like non-idle decoding protocol. And really, for each of this like ingredient, like faulty kind of systematic bias in the entangling gate, or measurement error, or some non-idle decoding, there's this kind of information has some stability. So this is like really what I mean by many-body physics of information. There's some information theoretic kind of capacity of this entire protocol to generate this long-range entanglement that is robust under this deviations. And in some sense, this protocol maps to imaginary time evolution, and deviation from the ideal protocol translate into like reduction of infinite beta to a finite beta. So, so now that I gave some concrete example of this kind of transition behavior, I want to talk about more general framework to capture this transition. So what I stated earlier can be rephrased as our capacity to convert noisy short-range entangled state into long-range entangled state, meaning that this noisy short-range entangled state is like a resource, and it's like its capacity to be a resource is gone beyond some error threshold. So now the question I can ask is, what is the noise threshold for the state to be resource, or maybe verifiable? Because if you imagine preparing a SPT state in a quantum simulator platform, you can ask, oh, how can I verify whether this is SPT state? Actually, our ability to verify whether it's SPT state or not is exactly tied to our ability to convert it into a long-range entangled state. So they're in some sense very similar. So we need some like a framework to understand entanglement structure of the mixed state. So one of the motivation was that like in the previous works on like kind of undecoherent setup, people thought that this a non-local order parameter of the like symmetry-protected topological order state is the reason why we can decode kind of like long-range entanglement. So in this like a two-dimensional setup, if you think about this string order parameter, which is product of 2z on the red qubit and product of x in the middle, this always take a non-zero finite value. Meaning that if you measure all the like white ancilla qubit, then you're going to induce kind of long-range correlation. However, if we introduce a decoherence on this like white ancilla qubits, like measurement error, then you can show that any like non-trivial, any like this string order parameter for any string is going to decay exponentially with the system size, with the size of the string. So looking at this, it seems like we are not going to induce any long-range correlation if there's a decoherence. However, in the previous example, I showed you that like even if there's a decoherence, you can still decode and get the long-range correlated cat state. So since this like physical observable doesn't show any transition behavior, you can ask what kind of theoretical probe will allow us to like capture this information theoretic transition. So although like this kind of average string order parameter will become exponentially decaying after decoherence, the conditional correlation won't be. So what I mean by that is, if you like for the decoherent state, if you like measure the correlation function between this red qubits conditioned on a specific measurement outcome, it can still be long range correlated, even if its sign can be now kind of randomly flipped. So decoding in this case will be finding a spin flip transformation to cancel the sign structure of this conditional correlation. So in this sense, this kind of averaged magnitude of the conditional correlation is providing an upper bound for this non-local order parameter that can be, and even if like this non-local order parameter decays exponentially, it doesn't mean that there doesn't exist any kind of decodable long-range correlation. So instead of like a left-hand side quantity, this yellow box quantity is really a true upper bound for utilizable correlation. And so the question is how to capture then the transition of this quantity. So the idea is that like I don't want to really think about all the decoding protocol because those are kind of complicated and you may get different transition behavior depending on what decoding protocol you use, as I showed in my previous example. So I want to focus on density matrix because in principle, all information is already there inside the density matrix. Because if you think about this protocol to prepare the cat state, like you have this decoherent density matrix of the short range entangled state. And this measurement and decoding protocol is really kind of like auxiliary. One can say that like this non-local order parameter is in some sense some non-trivial function of decoherent density matrix. So how do I study the information inside density matrix? As a like condensed matter theorist, we are familiar with the pure state, and mixed state is often some kind of object which is kind of hard to deal with. So what I do is simply vectorizing a density matrix in such a way that 2 to the n by 2 to the n like a density matrix becomes 4 to the n by 1 vector living in the double Hilbert space. So in some sense, like if you have a density matrix, when you map into a pure state, it's now a pure state living in the like bilayer system. And when you have a decoherent density matrix, this decoherence channel will act like some kind of coupling between these two layers. So now with this kind of mapping, the problem reduces into the study of pure state. So now in this double Hilbert space, I want to use a diagnostics for SPT state that has been well studied in the pure state context. So when we have some symmetry-protected topological order, it's characterized by anomalous boundary theory. So when we have SPT state in contact with a trivial state, the boundary between them should have some long-range correlation, either by symmetry break, spontaneous symmetry breaking, or being gapless. For example, in 1D cluster state, at its boundary, it must have a spin 1/2 gapless, like a zero mode, or in a two-dimensional topological insulator, when it's contact with vacuum, it's going to host like two counterpropagating gapless nodes. Or there's another diagnostic, which is a non-local order parameter given by the composite object of flux insertion and the non-trivial SPT pumped at the boundary of it. But here, I'm going to focus on really the first diagnostic, which is anomalous boundary theory. So when we have this anomalous boundary theory, at the boundary, if you measure the correlation function between these two, like X mark on the left-hand side, it's going to have a non-trivial behavior. But you can imagine doing some weak rotation of this correlation function in a sense that now, up to tau equals 0, you have this your non-trivial SPT state psi, but from tau 0 to infinity, you have this trivial state omega. And they are relayed by a weak rotation. But if you think about correlation defined by the right figure, it's going to look very weird because it's a correlation sandwiched by a two different wave function, which is not something experimentally accessible. But still, this is a very powerful theoretical diagnostics to tell whether a certain state is topologically trivial or not. And actually, I've shown that this strange correlator, which is really strange in the context of pure state, is going to prove something very physical in the context of double Hilbert space. So now, if you have a SPT state under decoherence, in the double space picture, you have two copies of SPT state, whether the other copy is kind of conjugated. And now there's the decoherence. And starting from the state with a fixed point, you can show that this doubled state of the decoherent density matrix is given as the ground state of this kind of locally interacting Hamiltonian between two layers. So the question really reduces to what phase we get for a given Hamiltonian. And to detect this, to get some phase transitions, we can define these two different types of strange correlator, whether the type 1 strange correlator is sensitive to the SPT-ness of individual kind of single layer, and type 2 strange correlator is sensitive to the measuring the SPT-ness of the entire layer. And actually, one can show that this type 1 strange correlator is exactly similar to the conditional correlation I mentioned in the previous step. So although this type 1 strange correlator is physically nonsensical in the pure state sense, you can show that this type 1 strange correlator is actually providing a upper bound for any decodable correlation. The reason is that this thing sandwiched, this bra state is a product state, which is naturally up here if you imagine measuring your SP state in a some product state basis. So think about how we actually kind of extracted like long-range entangled state starting from the SPT state. We were measuring the half the system in a certain product state basis, right? And that's basically similar to contracting with like a product state, like in the type 1 strange correlator. So like this kind of weird object is actually capturing the decodable correlation. Sorry, is there any question?
Jim, probably I have a trivial question. I remember apart from type 1 and type 2 strange correlator, Jim also proposed another type of strange correlator, which probably only works for a strong disorder case because they're just considering some disorder average version of the SPT. I wonder, is there any correspondence with that strange correlator versus your type 1 or 2 strange correlator?
So actually, like I and Chenke are trying to understand the paper, and we don't really understand what kind of. Yeah, I don't think their strange correlator is really related to what we are doing, and I don't find that definition to be very physical. Yeah, I mean, probably you're gonna get same answer even if you ask to Chenke. So yeah, I don't think I actually understand the paper well.
I see. Another question is about a Cho double picture. So the issue is we can always map that density matrix to a double layer wave function. But if I just write down a variational wave function of the double layer with the corresponding symmetry, they may not revert to the reasonable density matrix because you need to make sure it is semi-definite. Yeah. So this mapping is actually overcomplete. And I wonder, will there be any loophole?
Yeah, so there is something I'm working with my collaborator. So there's a positivity constraint on the density matrix as well as like hermiticity. It's a strongly constrained what kind of topological phase you can get in the double Hilbert space. If you think about kind of physically sensible density matrices. And for example, according to our criteria, if the density matrix has some notion of like gap, like a short range correlation, then it cannot have anything new in the sense that all the SPT structure of the density matrix or the density matrix in the double Hilbert space must be inherited from kind of single wave function level. So according to our like criteria, like intrinsic like average SPT is not possible unless you give up the notion of gap. So I think, for example, in other people's work, trying to work on intrinsic, saying that something new can emerge in the density matrix, that's only possible because now you're not talking about kind of gap state anymore.
Yeah, they begin with some intrinsically gapless SPT.
So yeah, and in the case of gapless SPT, there's no surprise that like when you think about density matrix, there's something new emerge, which is, I mean, things are kind of ill-defined in a long-range correlated system anyway. For example, you can imagine a situation where you combine like ensemble of two totally different wave functions, right? Because like density matrix is an ensemble of states. You can think about like 50% probably you get like SPT1, 50% probably you get kind of trivial state. Then that density matrix will have kind of correlation structure of both disorders, like trivial state and the SPT state, right? Like how can you how can you classify such a state? Like the density matrix that has non-trivial correlation for both order and disorder parameter is going to be gapless. So I think one has to be very careful when you're defining the notion of like phases and kind of classification when it comes to the density matrix. And I think if you're not like being careful, you're probably going to make some like, inconsistent statement.
All right, thank you.
Okay, so now like these like type 1 and type 2 strange correlators can be understood as the following. So as I mentioned, type 1 strange correlator is measuring the SPT-ness of kind of single layer. So when type 1 strange correlator is non-trivial, it means that like a two kind of double states are kind of decoupled. And when type 2 strange correlator is non-trivial, it means that overall there is some kind of non-trivial kind of topological structure in the double space. And interestingly, these two order parameter undergoes transition at a different critical point. So if you're in the so you can basically divide this kind of phase in the double Hilbert space into three parts. The first one is a decodable phase. So as long as type 1 strange correlator is finite, information can be decoded in a sample efficient manner. But if you're in this like the middle phase where type 2 is non-trivial but type 1 is trivial, information is there. If you just repeat the experiment exponentially many times and get the full state tomography of the density matrix, you can say that what you prepared is something non-trivial, but it's going to be very, very difficult. And there's like a final phase where information is gone, totally leaked out to the environment. So like this like a first phase, the decodable phase, exactly where our this conversion process from the noisy short-range entangled state to the long-range entangled state using measurement and decoding was possible. And this second phase can be understood maybe sense similar but not exactly to the black hole information paradox, where when we know that like if we know all the like unitary dynamics within the black hole, then if something is fallen into a black hole and got like fully evaporated into Hawking radiation, by collecting all the Hawking radiation, in principle, you should be able to kind of recover your original like information psi. But it is like possible in principle, but exponentially difficult, meaning that like from the computer science kind of language, it's basically impossible. So this the second phase is something like that. Information is there, but it's gonna be very, very difficult to extract that information. And so until now, I talked about symmetry-protected topological order, but you can do exact same thing for topological orders like familiar like toric code, for example. And those kind of topological order is like actually encoding some like robust quantum memory in a sense that this logical information can survive even under decoherence. So, but like previous studies, like I think Dennis, like Kitaev and Preskill and Landar, they try to understand this like error threshold based on the decoding algorithm, the threshold of the maximum entropy decoding algorithm. But you can ask whether you can study this like in a fundamental error threshold in a way kind of independent of the decoding algorithm. So maybe I can skip some details about toric code. I mean, I guess, so the idea of the toric code is that this the logical space of the toric code is a ground state of this Hamiltonian, where A is like the product of this 4 Z terms and B is the product of this 4 X terms around the pocket. And you can show that the ground state of this Hamiltonian is a 4-fold degenerate. And this degenerate space can be used to encode some 2 qubits of information. And now you can ask when this like 2 qubits of information, logical information, disappears under this dephasing and spin flip errors. So as I mentioned, like these people have shown that like even if there is some kind of like noises, you can use some decoding algorithm, maximum entropy decoding algorithm, such that you can correct those errors in the thermodynamic limit as long as error rate is below this like 11%. And I'm interested in fundamental bound of decodability. So as in the case of SPT, I can go into a double Hilbert space as well. And in the toric code case, it's now going to be like a 2 toric codes, and the decoherent channel maps to like anion tunneling. So and like you can like map this situation into the study of the like Ising model, because under Kramers-Wanier duality, the toric code maps to like a paramagnet, and the decoherence anion tunneling maps to like a ZZ decoupling. So initially you have a system with like a 2 Z2 symmetry, and then under this like the 4 spin coupling, like the diagonal Z2 symmetries got spontaneously broken, and you're gonna have some like a phase transition. And like if you map things back into a toric code situation, it basically means that two copies of toric code undergoes a phase transition into a single copy of toric code. So in some sense, this can be thought as like a spontaneous, from the toric code perspective, you can think of it as a kind of spontaneous kind of restorations of like a one-form symmetry. But from the like Ising model perspective, you can think of it as a spontaneous breaking of like a Z2 symmetry in the double Hilbert space. And now what it means is that the quantum information that could be like efficiently decoded, the logical information, is gone after this threshold. So one thing I want to mention is the following. As I mentioned earlier in the slide, any quantity linear in the density matrix, decoherence does not induce any transition behavior because like this logical information, which is non-local string order parameter, will immediately suppress exponentially. So the quantity linear in the density matrix is not capturing anything interesting. On the other hand, information-theoretic transition happens in the quantity non-linear in the density matrix, such as von Neumann entanglement entropy, which is a trace of rho log rho. And double state formalism is actually not capturing this quantity like logarithmically nonlinear. It's capturing some first non-trivial nonlinearity, which is kind of quadratic in the density matrix. So, but like what it means is that the threshold provided by this double formalism is overestimated because the nonlinearity, which is precisely capturing the our information theoretic capacity, is like a rho log rho, not like a rho square. So in principle, one has to all this formalism I talked about is really providing some upper bound, but actually for SPT case, it's a totally different story because I'm still using the product state and the single density matrix. So, but when it comes to the topological order and trying to capture transition this way, it's a different story. So, in principle, if you want to capture a fundamental error threshold, you have to calculate coherent information for your quantum system using the von Neumann entanglement entropy, not like a Renyi entropy. So coherent information is a quantity that quantifies the decodable information in the logical space. So it is defined as the following. This Q, red box, is your toric code state. This R is a reference qubit. You start from an initial state where all the logical qubits in the Q is maximally entangled with the reference qubit. And then now, this toric code state is undergoing a decoherence, which is basically a coupling to environment. And then you're asking the conditional von Neumann entanglement entropy of the reference state R, condition on this toric code state Q. If they are maximally entangled, if you know all the a toric code system, that means that this conditional information will be negative because that's how kind of quantum information is defined. But if this quantity is 0, it means that you know nothing. You have no quantum information about system R, even if you know system Q. So this coherent information is really the metric, and these people have shown that the decoding, perfect decoding, is possible if and only if the coherent information remains robust under decoherence, because this coherent information does not change under any kind of action of channel, and decoding operation is also the channel action. So if decoding is possible, this IC should stays as its maximum value, meaning that if IC after decoherence kind of get reduced, then you're losing that much information that's decodable. So in this plot, I was showing this coherent information that's calculated exactly using analytic diagonalizations of the decoherent density matrix. And one can show that the coherent information is undergoing phase transition at this the 0.11 by 0.11, which is exactly what's obtained by Dennis and other people from just a decoding perspective. So what it means is that the fundamental error threshold is actually saturated by this maximum entropy decoding for many of the CSS codes. And the formalism developed in my paper to get the coherent information exactly is completely generalized to the ZN like topological code or many other CSS codes. So I believe that for those CSS codes where like stat mapping for the decoding algorithm is possible, probably those decoding algorithm is like saturating the maximum, the fundamental error threshold that can be obtained by exact calculation. So this is the exact analytic expression where PI is given as a like some weird quantity. So the numerator is a partition function of the random bondized model for given bond configuration S and inverse temperature beta. And inverse temperature beta is related to the error rate P in a certain way. And I'll refer to this paper, which was posted last night, if you want more details. So, so in this talk, I talked about like various kind of information theoretic phase transitions. And this is really the beginning of like, I think, the exploration along this direction. There can be many interesting directions, such as like getting a fundamental bounds more precisely for various other kind of SPT phases or other like a quantum codes. And so far, I only talked about the SPT case with faulty measurement or topological order with perfect measurement. But actually, you can think about topological codes with faulty measurement by embedding that into like higher dimensional SPT phases. And similar framework can be used to understand why a single shot decoding is possible for some of the topological codes. So yeah, so these are my wonderful collaborators for this papers. And yeah, thanks a lot.
Okay, thank you. And are there any questions? Yeah, actually, I have a question. There's lots of decoherence-induced phase transition, like the Tori code case, or the phase transition nature is pretty classical. It's always reminiscent of the classical easy mode at finite temperature in the same dimension. I wonder, are there any phase transition in this literature where the phase transition is indeed quantum?
Right, that is a great question, but the thing is that when you have a decoherence and think about decoherence into phase transition, it's kind of mathematically mapping into a boundary criticality problem. Although I can phrase them into a phase transition still happening in the same dimension, and I can think about this Hamiltonian. But what's interesting about this Hamiltonian is that this Hamiltonian at the critical point, it's like most of them has a Lipschitz criticality, meaning that you know, when you have a Lipschitz type of criticality, it's not exactly like a same dimensional quantum problem. It's like effective dimension is in some sense one dimensional lower. And actually, you can, for many of the example I studied, the critical point of this Hamiltonian, the wave function is given as the conformal quantum critical point, meaning that for this the 2+1D system, its wave function is given as a superpositions of components where each component's coefficient is given by a 2D classical Boltzmann wave. Another indication that the criticality here is a Lipschitz type of transition. So yeah, so I think all this decoherence-induced phase transition should correspond to some boundary criticality.
I see.
This is more obvious if you think about how from the density matrix formalism, you have like there's a space-time picture for density matrix. So this is along time direction, and decoherence acts like some kind of coupling between bra and cat. So decoherence acts like some kind of temporal direction kind of defect. And now you're interested in the correlation function on this temporal defect, right? So, so in this sense, any kind of transition behavior in the quantity that is so because like in this double Hilbert space, if you think about some correlation function, this is nothing but trace of rho O1, rho O2, okay? And if you represent rho by this space-time passive integral formalism, it's like you have a O1 here, and then rho, O2 here, and rho, right? And then like decoherence is really happening at this boundary. So yeah, it has to be really a boundary criticality.
I see. Cool. Yeah. Great. Another probably relevant question is like for local unitary preparation of SPT state together with measurement with post-selection, you demonstrate like in 1D, if I just slightly tilt the angle of the measurement, then there's no stable long-range order state. And in 2D, you can generate a stable cat state, but if you want to generate something like a toric code cat long-range entangled state, then we have to go to higher dimension. In 3D, what type of theory to give you a lower bound on in what dimension can you have a stable cat state under such type of preparation?
Oh, so this is tied to the fact that 2D cluster state is protected by zero, so I didn't mention it, but 2D cluster state has two symmetries. The first one is Ising symmetry on this vertices. And second symmetry is a one-form symmetry on the edges. If you think about loop operators, for any kind of like a loop configuration, any loop of like a product of X, the state is invariant if that loop is acting on the edge degrees of freedom. And what's known is that one-form symmetry is robust under any error.
I see.
So the reason is the following. So I told you about when there is a frustration, it makes it hard to assign a consistent spin configuration, right?
Yeah.
But I mean, you don't have to be confined to a specific pocket. When you have a loop-like symmetry, there's this loop, there's this loop, there's like this loop. There's so many other loops that you can consider to correctly infer what consistent spin pattern should be.
I see.
So really, what makes the decoding here robust is the presence of a one-form symmetry.
I see.
And the fact that one-form symmetry is robust under this kind of small errors, decoherence.
I see. Cool. So like the
only,
other,
you have a zero-form symmetry, right? And zero-form symmetry immediately kind of trivialize even if you have just a single defect.
I see.
So the question here is, which degrees of freedom is decohered? In the case of preparing the cat state, what's decohered is a one-form degrees of freedom, which is the reason why this protocol is robust. But in the preparation of the 2D toric code, or generally 2D topological order, so you're starting from the same cluster state. The only difference is that you're measuring the vertices, right? When you're preparing the toric code. But because the measurement error on the vertices translates into error decoherence of the on-site Z2 symmetry, which is very fragile under decoherence, preparing toric code or preparing topological order using this kind of protocol is intrinsically fragile.
I see. So here's something like if I measure the matter field which live on the vertex with some type of error, it's something like I slightly, for the original SPT wave function, slightly break the zero form symmetry, but for zero form symmetry, one is broken, then that's totally trivialized. For one form symmetry, usually you weakly break it, lots of silent properties is still there.
Yes.
Yeah, okay, cool.
Yeah. And that's actually the reason why 3D SPT, protected by one form cross one form symmetry, is robust under any type of decoherence. Yeah.
I see. Great. So any other questions? Okay, if no question, let's thank you again.
Yep. Thanks a lot.
Thank you.